This video is about galvanic cells. So galvanic cells are also known as electrochemical cells. They're used to demonstrate the flow of electron from one species to another, and they're called electrochemical cells because they're changing chemical potential energy into electrical energy. It's basically how batteries work. So let's have a look at this complicated scenario here. This is a galvanic cell. It consists of two half cells, a salt bridge connecting the two half cells, an anode, a cathode, which are both electrodes, which are dipped into electrolyte solutions, and they're joined together with a wire so that the electrons can flow. Because remember, an electric circuit needs to be a complete circuit. And you can see here, if you follow it around, it creates a complete circuit. So we can get electricity flowing. And this is why the voltmeters here. If we have a look at this galvanic cell, you'll see that there is the anode, which is made of copper. And the reaction that's occurring at the copper is that the copper solid is disintegrating into, or breaking down, into copper 2+ ions and 2 electrons. So electrons are being produced here at the anode, and they're going around here till they get to the other electrode called the cathode. And I'll be explaining these terms in a minute, but I just want to give you an overall picture. So this cathode here is made of silver. So what's happening here is silver's going to be coming out of solution, so out of the silver nitrate. These are the silver ions that are coming out of solution. They're going to be reacting with the electrons that are coming down to form silver solid. So you get a build-up of silver crystals here on the cathode. These two half equations here can be added together to get a full redox reaction here. But we'll go through that in detail and step by step now. So the essential parts to the galvanic cell are the following. You need the two half cells. So here we have the two half cells. You need two electrodes, one of which is the anode, one of which is the cathode. You need an electrolyte, and both of the electrodes need to be sitting in some form of electrolyte. There needs to be a wire connecting the two electrodes, and there needs to be a salt bridge. So let's have a look at all of those things in detail. So two half cells, here they are here, and you'll be doing pracs like this in class. So you've got an oxidation half cell, and you've got a reduction half cell. Remember, oxidation is loss of electrons, reduction is gain of electrons, and that's where the electrons come and move around. The contents of these half cells do not mix, and you can see here they're in separate beakers. They don't mix. Here are your electrodes, and here's your salt bridge, which is basically just a piece of filter paper which is being dipped in a salt solution. Okay, let's talk about the two electrodes that are needed. They need to be conducting, so they need to be made, they're generally made of a metal or of carbon, because remember, carbon conducts electricity. So the anode is where oxidation occurs. Remember, oxidation is the loss of electrons, and you can see here in this reaction, copper is undergoing oxidation, so it's losing 2 electrons. This has a negative charge due to the generation here, or the loss of electrons. The electrons are being generated and they move up out of the electrode. So this electrode will corrode, and that's what this picture's showing here, because what's basically happening is copper, this copper solid, is turning into copper ion. So it's going into the solution. So copper solid is no longer solid, it's ions, and the 2 electrons are whizzing up around the wire to the cathode, where reduction will occur. Okay, let's have a look at the cathode. Here we are, we have a silver cathode. This is where reduction occurs. This has a positive charge. And what happens here is you get a build-up of metal crystals, and the reason for that is you've got silver in solution, which is grabbing onto the electrons that's coming through. So silver plus an electron forms silver solid. And this is how you do silver plating. And if we get a chance, we'll do that in class as well. So the electrons are coming down the wire from the oxidation reaction, and now reduction's occurring. So the silver in the solution is grabbing onto that electron and forming solid silver. And you'll actually see that forming on the outside of the silver crystals. So we've got the anode, which is negative because it's producing electrons. This is where oxidation occurs. So the zinc here becomes zinc 2 plus and 2 electrons. Oxidation is occurring, electrons are being produced, and that is the negative electrode called the anode. The cathode is the positive electron, start again. The cathode is the positive electrode. This is where the electrons are being accepted and the reduction reactions occurring. So here these copper are forming copper solid when the electrons meet up with it. So Cu2 plus comes out of solution, grabs on to the 2 electrons to form copper solid. You'll get a build up here of copper on this electrode. And there's our picture again. Oxidation of copper. Oxidation is loss of electrons. This causes this to be negative, so it's the anode. And here we have positive, and the silver's being formed on the outside because of the reduction. Okay, the way to remember this is, we already know oil rig, now you're adding on an oil rig cat. Anode, oxidation is lost, reduction is gain, and that occurs at the cathode. An oil rig cat. Anode, oxidation is loss, reduction is gain, occurs at the cathode. Okay, the third thing we need is the electrolyte. The electrolyte is the solution that the electrodes are sitting in. This contains ions that are free to move. And it's important because it will maintain the balance of charge in the half cells. What do I mean by that? What I mean by that is that here you have zinc solid forming zinc 2 positive ions. So here we have 2 positive ions coming into the solution. What will happen is that negative ions in the salt bridge will come into this solution because they'll be attracted because there's a positive charge forming in that solution due to the build-up of zinc 2 plus. The nitrate here will balance out that positive charge because you don't want to have a charged solution. On the other hand, on this side, what's happening is that copper in solution is forming copper solid, so you're losing positive from this solution. So the positive in the salt bridge, which in this case is potassium, will enter this solution to replace the copper that's being lost. So basically the salt bridge is just there to balance out the charges in the electrolytes. Here again, zinc solid is forming zinc 2 positive. The solution would be charged positive, but the negative charged ion from the salt bridge comes in to balance that out. On this side it's losing positive charge, so the positive comes down to balance out that charge. Fourth thing we need is a wire connecting the two, and that's all we basically need. And here it shows that a light bulb, because there's electricity or electrons passing through that, and it's just for the electrons to move. Okay, and the last thing, which I've already pretty much spoken about, is the salt bridge that's needed. So you've got a salt bridge that can be made up of, it's generally something like potassium nitrate. something that's not going to be reactive, that's not going to form any sort of ionic solids or anything like that. What the salt bridge does, it completes the circuit and it provides electrical neutrality, and that's what I was talking about before. You're compensating for ions that are lost or gained during the redox reaction. So here we've got a copper electrode, and what's happening here is that you've got extra copper ions that are being formed at the electrode surface. So copper ions are being formed when this copper electrode disintegrates. So what's going to happen here, to balance out that positive charge, you're going to have negative charge migrating down the salt bridge to balance out that charge, and in this case it's nitrate. Okay, so when drawing a galvanic cell, you must include the direction of the current flow along the wire, the direction of the flow of the anions and cations in the salt bridge. The anode and the cathode must be labelled. The signs of the electrodes, positive or negative, must be labelled. The material from which each electrode is made of must be labelled. The electrolyte in each of the half cells and the half equations must be written. And the overall redox reaction as well. Have a look at an example. This is question 7 in your notes. A galvanic cell was set up by combining half cells containing lead and magnesium electrodes dipped into the appropriate nitrate solutions. A conducting wire and a salt bridge completed the circuit. After 3 hours, the 2 electrodes were removed and weighed. The mass of the lead electrode had increased, while the mass of the magnesium electrode had decreased. Draw this galvanic cell clearly indicating the following: the anode and the cathode, the ions present in the half cells, the electrolyte in the salt bridge, the direction of the flow of electrons, the anode reaction and the cathode reaction, the oxidation and reduction reactions, the overall cell reaction, and the oxidant and the reductant. So there's a bit there to think about. Let's have a look. So here I've just rewritten the main part of the question and pointed out the obvious bits or the important bits. So the half cells contain lead and magnesium electrodes. So we know what the electrodes are made out of, and they're dipped into appropriate nitrate solutions. What are the appropriate nitrate solutions? Lead nitrate and magnesium nitrate. Keep it easy for yourself. The mass of the lead electrode had increased while the mass of the magnesium electrode had decreased. That tells us exactly what the reactions are that are occurring. Let's have a look. Okay. So the mass of the lead electrode had increased. So what's happening there is that lead is coming out of solution to form lead solid. Okay? Because the weight is increasing. So these ions here are meeting up with electrons to form lead solid. So what's happening on the other side? The magnesium electrode mass had decreased. We've got magnesium solid becomes Mg2 plus 2 electrons negative. So what's happening here? Out of the electrode. And the electrons being produced are heading in this direction. That tells us basically what we need to know. We now know this here is the negative electrode. A negative electrode is the anode, and I can put a negative here. This must therefore be the cathode, and I can put a positive on this side. We're halfway there. Oxidation is loss of electrons. So this is your oxidation reaction. And reduction is gain of electrons. So this is the reduction reaction. This is a good point here to double check that your anode matches. An oil rig cat. An anode, oil, oxidation, loss of electrons. Double check yourself at that point. Make sure it's correct. Reduction is at the cathode. Correct. So both sides are correct. The electrons, we have to point out which direction they're moving in. We know they're moving in this direction. We'll just make that nice and clear. Now the only thing we need to do is work out the direction of the flow of the ions in the salt bridge. One of the easiest ways to work this out is that this is losing positive, so positive nitrates need to replace the positives that are going in this direction. So the only thing we've got left to do now is to figure out which direction the salt bridge ions are moving. The easiest way to figure this out is to look at the fact here that lead 2+ is disappearing out of the solution. So these positive ions need to be replaced with positive ions from the electrolyte in the salt bridge. Here you've got positive ions that are going into the solution. This is getting more and more Mg2+. So this is becoming positively charged. That will attract the negatively charged nitrate. Okay, so the last thing then that you need to do is write the overall redox reaction. It's just a matter of adding these two reactions together, ensuring that you make sure that the number of electrons are equal. They are here, so that's simple. So I'll just write it. I'm running out of room. Mg solid plus Pb2 positive goes to, that should be aqueous, Mg2 plus Pb solid. That's an aqueous. And that's your overall reaction. Nice and easy. Okay, so the only thing we need to think about here is which is the reductant and which is the oxidant. Now remember, the reductant causes the reduction of another species. So magnesium here is the reductant. It causes the reduction of the lead ions. The lead ions are the oxidant, or the oxidizing agent. They cause the oxidation of the magnesium solid. Okay, I suggest you have a little go at question 8. So pause it here and I'll run through the answers. Okay, again I've highlighted the important bits of the question. Iron metal is dipped into a solution of iron sulphate and it's going to form a coating of iron. So iron metal forms a coating of iron. NaCl is your salt bridge and zinc sulphate is one of the electrolytes. So this is the sort of thing you want to draw. You've got your iron metal and iron sulphate as your electrolyte. This is zinc sulphate, so keep it easy. Zinc sulphate here, make it a zinc electrode. The easiest thing is just to match your electrolytes with your electrodes. And of course you've got the sodium chloride here in your salt bridge. So iron metal is forming a coating of iron. So what's happening here is that you've got ions are coming out of solution to form iron solid. So these here are forming iron solid because they're accepting an electron from this reaction here. So what's happening on this side? It must be the oxidation reaction to produce those electrons. So I've got Zn solid is becoming Zn2 plus aqueous plus 2 electrons. So we're producing the electrons on this side and they're coming over there. Just make sure that you really clearly mark your direction of your electrons. Electrons are being produced on this side, so this must be the anode, A negative oxidation. This is my oxidation reaction. It's producing electrons at the anode, so that's correct. This is my reduction reaction. And I'm receiving electrons to form iron solid. So we've got sodium chloride, so we've got Na positive and Cl negative. I always think the easiest way to look at it is see where the positives are moving. This is being depleted of positives, so positives need to be replacing. So you're going to have sodium ions, positive ions moving in to replace the lost ions, and on this side you're going to have Cl negative anions there, which are coming in to balance out the Zn2 plus ions that are being produced from the breakdown of the zinc. This of course is going to be the one that's depleted, and this is the one that's going to get rid of the outside. Need to write an overall reaction, so again make sure these electrons are even, otherwise multiply the reactions by what they need to, and the overall reaction will be Fe2 plus Zn solid, Fe solid plus Zn2 positive aqueous. And if you want to point out, and the last thing you need to look at is the fact that zinc here is the reductant. It's causing the reduction of ions, and Fe2 plus is the oxidant. It's causing the oxidation of zinc solid. Okay, so there's a few questions there that you can get on with now.